All right. You tell me. Tell me if there's any problems. You started with your original. Secant originally is all real numbers except where x is equal to n pi over 2. And you must save it this way. Except where x is equal to n pi over 2, where n is an odd integer. Set these. Okay, so why is yours?
No, my C. It's a different question.
Oh, it's a different question? You have a different one.
We have one.
So, Olivia, does it look better now? Olivia, does it look match yours now?
Yeah.
Okay, because didn't you say you didn't have it? Didn't have that answer?
Well, it was a different sheet.
No, I know. So I'm asking, do we look okay now?
Yes.
So start with your original tangent. Remember, tangent and secant work the same. Cosine and cosecant work the same. And then set it equal to whatever it is you have there in front of x and solve for x. Keep the same exact piece right here.
Oh.
Yeah.
Where's the range?
Hang on 1 second.
Right there. Negative infinity to infinity.
Negative infinity to infinity. Probably not that noticeable. Tangent, the range is infinite.
Wait, so the x equals n, where n is odd, that's the...
This comes from here. That's the same, whatever it is in the original, you bring that part down.
I was just making sure.
Uh-huh. You bring that down. Good? You have questions? No?
So let's predict the weather tomorrow.
Well, let's work on this right now. So number 2, we start with the cosecant. Cosecant says real except where x is equal to n pi, where n is any integer. Set them equal. You don't care about a reflection or anything else. All you care about is the domain. And set them equal. And so then x, the domain will be real except where x is equal to 2n pi, where n, because you're keeping this one, that's why we have this 2 in here. It just works out that way. So you're still keeping all the even ones like we did yesterday when we looked at the 0, the 2 pi, the 4 pi. It still works the same. Your range is still 1. We didn't change your amplitude. Good. Stop me if you have any questions. Okay, secant. Work off of your n pi over 2. X is equal to n pi over 2. And this time you changed your amplitude, so that's going to change your range. Again, keep the same descriptive with qualifier here, where n is any odd integer. Now when you graph something like this, don't forget you're graphing in radians. So you wouldn't use your pi, you'd be using like a 1, 2, 3 type thing, 1, 2, 3, 4. And you could set your axis up just like that to make life easier. Okay? You change the amplitude on this. Start with your cosecant. Real except for where x is n pi, n is any integer. And set it equal to the 2 pi x. Right okay with this? It's pretty the same pattern. I kind of wanted you to get used to doing without having to graph, without seeing it on the graph. You have 2 of them to memorize. Remember, the 2 c's are exactly the same. And the tangent and the secant are the same. So the easiest one to remember is the tangent. Because the tangent is you can't use 90, you can't use 270. That's the n pi over 2. So that makes you the same as the secant. So therefore, the cosecant is the n pi one. So if you just gotta, memorize it or find a way to help you memorize it. So we're okay with these?
Yeah.
Okay. Let me just.
No. It's reflected over y equals x.
Very good. An inverse is a reflection over the line y equals x. Okay, so we have to keep that in mind. Now, because it's a reflection over the line y equals x, then that means you're going to swap these out. These are interchangeable, as well as the domain of this guy now becomes the range of this guy. The range of this one now becomes the domain of this one. Right? Because this is the domain of all the x's. So we swap out the domain and the range as well. Okay? So when we do this, we need to start off with a certain condition. For something to have a true inverse, it has to be a one-to-one function. Okay. Now remember back when we looked at a parabola and we had to take the inverse of this parabola and we said it doesn't pass the horizontal line, it had to pass vertical line test and it had to pass the horizontal line test to be one-to-one. What did we do when it didn't pass the horizontal line test and we wanted to make an inverse? We restricted the domain. So we said either use the increasing or use the decreasing, right? We cut it off right before it fails the horizontal line test. So we either used just the increasing and then we made an inverse out of it, or we did the decreasing and we made an inverse out of the decreasing. Well, the same thing is going to happen with your trig functions. Because if you think about especially your sine curves, the curves itself, when they come over the little hump there, they fail a horizontal line test. So what we have to do is restrict your sine curves. Now, let's start with I'm not going to have this really. Okay. So if we do a sine curve, I gotta move this down, I'm sorry. If we do a sine curve here, your basic sine curve, let's take a look at your sine curve. I'm going to separate your sine curve into quadrants. This is quadrant 1 from 0 to 90. This is quadrant 2. This is quadrant 3. This is quadrant 4. Now, if I go backwards, think of your unit circle. If I go backwards this way into the negatives, this is quadrant 4. Don't these keep repeating in a cycle? 3, 2. So isn't this a continuous curve? 1, 2, 3, 4, 1, 2, 3, 4. It's forever and ever and ever, right? Now, what's the problem with this sine curve? Does this sine curve pass a vertical line test?
Yes.
But not a horizontal. So as soon as we fail a horizontal line test, we have to cut this off. Now, key to this is everybody is going to use quadrant 1. We're going to restrict this for everybody in quadrant 1. Now, here's what we get out of this. My unit circle goes from 1 to 4, right? Where is sine positive from 1 to 4? What quadrants? What quadrant is my sine above the 1 and 2? And sine is negative
3 and 4.
in 3 and 4. Now, we're going to restrict this sine curve. We want to make a true inverse out of this. So what we want to do is come around here and stop this guy from failing a horizontal line test. God bless you. Now, we can only go this far. So, but we notice, do we fail a horizontal line test if we go this way?
No.
So we go right here until we fail a horizontal line test. So, go ahead.
Oh no, I didn't understand why I did that.
Because we need this to pass a vertical line test and a horizontal line test. So we always start in quadrant 1. We travel along quadrant 1, but we can't come over this little hump, so we stop it. And we notice if we continue the other way, it could come down here, but we can't go any further. Yes?
So is it like phase shift, like
No,
pi over 2?
no phase shift. These are just regular, we wouldn't phase shift on these. Your inverses, we're not going to throw you a phase shift at this.
Not at all.
Not at all.
Promise.
Promise. So now, tell me where sine, so if I restrict this domain, I have to restrict my domain from negative pi over 2 to positive pi over 2. Right? I have to stop right there, start there, and stop there. Because otherwise I'm going to fail a horizontal line test. And I can't make an inverse if I fail a horizontal line test. Now, if you take a look at this little piece of curve, now with your restriction, where is sine positive? Which quadrant? 1. Where is sine negative? 4. So sine is positive in 1, negative in 4. So if I give you a unit circle, sine is positive up here, sine is negative down here, under a restricted domain. So do you see what happened when we did this restriction? We no longer have 2 quadrants of positive sine. We only have 1 quadrant of positive sine. So you got your calculator handy? Now we know the sine of 30 is 1/2, right? According to this, we should have 2 angles that have a positive 1/2. We should have this angle, and we should have this angle, right? We should have 2 angles that have a positive 1/2.
Oh.
So let's ask your calculator. Second sine. What angle do you have that has a positive 1/2 for sine?
30.
This is where your arc comes in. Arc, sine. Give me an angle whose sine is 30. But somehow it didn't tell me 150, did it? It didn't tell me this angle. So your calculator only works off of a restricted domain. Okay? So let's try something else. I know down here, this is the sine of, in the second quadrant, God bless you. This is the sine of 210. Just put in your calculator sine of 210. Does it say negative 1/2?
Yep.
Okay, and we know there's another negative over here, right? Now, let's ask your calculator, arc sine negative 1/2. What angle in a restricted domain has a sine of negative 1/2? Ah, here's my restricted domain, and here's my negative 30. So, you see how smart your calculator is? Your calculator, remember way back when we had that little exercise and we were graphing inverses, and we did draw inverse on your calculator, and your calculator can only draw a true inverse? Well, your calculator can only do a true inverse when you say arc. Arc sine, second sine, arc sine, and sine negative 1 are the exact same thing. That says, give me an angle whose sine is. But when it does that, it only gives you 1 angle, and it only gives you the restricted angle. So when we work with an inverse, and we want to know what angle is this, we can only use my domain to be restricted from 4 here to 1. So we're negative 90 to positive 90. That is the only domain we can look from. And your calculator confirms that for us. It's not over here. It didn't give me this angle over here. Yeah, I know the sine of 210 is negative 1/2. I know the sine of 330 is negative 1/2. But it doesn't look out here at all. It only looks right here where your restricted domain is. Okay? Yes.
What are we looking for?
Well, we're looking to make an inverse out of this. If you look a little further down on your paper, did I draw the inverse on this? No, I didn't draw the inverse.
Say short number.
We're looking to draw the inverse on this. See this little thing down here?
Is that the
This is
restricted
the true inverse. This is your restricted domain for a true inverse. Well, now, notice,
So is that the sine curve? Because that looks like what we drew.
well, if you take this It's a little difficult to visualize. If you take this and you put your line y equals x through here, this has to be reflected over this. So that's where it's coming out like this. See it? It's coming out like that.
Looks kind of like tangents.
It kind of looks like a tangent, but see what it's doing? It's reflecting it over the line y equals x.
Okay.
I'm not going to ask you to graph that. All I'm going to ask you to do is be able to restrict your domain and find me a restricted angle whose sine is 1/2, whose cosine is -1/2. So in other words, if I say to you, arc sine 1/2, you will say, well, arc, that's my inverse, I'm restricted to 1 and 4. In 1 I'm positive, in 4 I'm negative. So if I want this to be positive, I want an angle from quadrant 1. So it would be 30. If I say arc sine -1/2, I'm restricted to 4, according to this. So I want an angle down here. Now don't forget, because this goes from negative pi to positive pi, I can't say 330. That's out of my domain. I have to say -30.
Oh, okay. So you can't say.
Your domain is just this now. Your restricted domain is this.
So it's never gonna be like more than 90, right?
It is, no.
No.
On this, no. On
Okay.
sine and tangent, no.
Oh,
On cosine is a
cosine
little
is-
different.
Okay.
Cosine's a little different. Now, technically, this is what we do. Watch. Here's my sine restricted curve. My domain says -pi/2 to +pi/2. My range still says -1 to +1. Now, Johan said before, when you do an inverse and you do a reflection over the y equals x, don't you interchange the x and the y?
Yep.
So therefore, when I do a restricted domain, when I do an inverse for sine, my domain becomes my range. My range becomes my domain. If I'm going to graph this, I have to interchange everything. Now, the hard part is, if you take a look at where this is drawn, see the inverse on the bottom? I'm going to move this, but I have to erase all this. Look at your inverse on the bottom of that page. Normally, didn't we go out to pi/2? This is your true inverse drawn down at the bottom. I'll move this down in a second. But just watch up here for a minute. We went to pi/2. Where is 1? If I was putting the value 1 on this line over here, on my x line, where would 1 fall?
Or,
Yeah, less than 90, right? 90
Yeah.
is pi/3.14 divided by 2. Figure 3 divided by 2, 1.5. So 1 is going to fall over here somewhere, right? So aren't you short of pi/2 when you draw your inverse? Because you had to revise. When you do an inverse on a line, I give you a line. I say, find me an inverse. You interchange your points. You make me a reflection over here. You're on the same axis. It's not a problem. When you do an inverse here, you went from putting your angles on quadrant X and your numbers on Y, you went to swapping those around. But you got to plot them on the same graph.
so your
So that's why it looks a little bit different.
so your y-axis ends up being your x-axis,
Yes.
basically.
But you're not changing it, so you have to adapt to it. Now, I wouldn't ask you to graph it, but I would ask you to be able to give me the sine's new domain and the new range. So if I ask you for the domain of an inverse sine, you restrict your sine curve, right? And then you swap your domain and your range. Do you see it?
Yep.
Okay. All right. So here, they're giving you the new domain and the new range of an inverse sine. And we found this ourselves. We found it and we inverted it. We took the inverse of it. So again, what I was saying was, if you took a point for pi/2, the sine was 1, wasn't it? So now I'm going to be 1 pi/2. Pi/2, we said, is like 1.5. 3 divided by 2, 1.5. So this is my 1.5. Here's my 1 somewhere. Probably like over here somewhere. And my pi over 2, wouldn't that be up here? A little higher than the 1? This is this new point. Graphed on the same axis. I'm not going to ask you to graph it, but I am going to ask you to understand what's going on. And you should be able to. Okay? When you take an inverse, don't you swap the x and the y?
Yep.
So aren't I swapping the x and the y?
Yeah, from that on its side, it looks like a sine curve.
Okay. All right. All right. I'm going to pass cosine for a minute. I'm going to drop down to tangent. I'm going to drop down to tangent. Tangent is easy.
Oh, we don't know.
You should have tangent, don't you?
Yeah, we do. Oh, we don't have an axis.
I'm not very
The one on your spreadsheet? All right, so draw me a little axis. Draw me a little axis. And let's draw the tangent curve. Where's the asymptotes for tangent? The domain is real, except when x is n pi over 2 and is an odd integer. What's the range?
Negative infinity, positive infinity.
Good. So, I know right here, I know right here, I know right here, I know right here, I can't use. So my tangent curve goes like this. Right now, I'm going to have to restrict my domain so that I pass a horizontal as well as my vertical. This passes a vertical, right? Now I got to pass a horizontal line test. This is quadrant 1, this is quadrant 2, 3, 4, and this is 4, 3, because I'm going backwards, 2, 1. Now, everybody starts in quadrant 1. Am I good with this part so far? Did I fail a horizontal line test? No. So I can't pass over this because here's my asymptote. So it forces me to come backwards. Good. Did I fail a horizontal line test? No. Now if I go over here to this guy, oops, I will fail a horizontal line test. So look how nice tangent is. It has a natural domain, doesn't it? Yeah. And the domain just happens to be almost the same as sine. So where is my restricted? Write this down. Restricted domain for tangent. What's that little section right there?
Negative pi over 2.
The pi over 2. Almost like the sine. What's the difference? Ah, the parentheses. Good. Good, Ashley. In a tangent, in a sine, I can use the sine of 90. But in a tangent, do I have a tangent for 90?
No, you do
So
not.
the only difference here is this. So tangent, therefore, uses 1 and 4. 1 and 4. 1 it will be positive, 4 it will be negative.
Tangent's my favorite inverse.
It's
But it's my
perfect.
least favorite.
Tangent is perfect. It's right there. Right. Okay? Now, so let's back this up now and go back to cosine.
I have a feeling cosine's going to give us a tough time.
Ah, no, not really.
Gives me a tough time.
Okay, so let's do your cosine curve. Let's do your cosine curve.
What would you say?
So here's my cosine curve. All right?
Yep.
Again, I'm going to separate these into quadrants. Quadrant 1, quadrant 2, 3,
4.
and 4. And if we go backwards, we came, guys, come on.
4.
This is a very hard concept. I do not want to hear I don't understand it if you're going to spend your time talking.
I do.
And then backwards. Now, we said got to pass a horizontal line test as well as a vertical. And everybody starts in quadrant 1. So in quadrant 1, oops, can I go backwards?
No.
No. So I have to cut it right there. So I travel along my way, and I come down, whoops, got to cut it right here. So what's my restricted domain for cosine?
0 to pi.
0 to pi. What quadrants am I in?
1 and 2.
1 and 2. Where is the cosine positive?
1 and 4.
Blah, 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 in your restriction.
Oh, 1.
First, everybody's positive in 1, right?
Yeah.
And then negative in 2.
I thought you just meant in general.
Yeah, no, I'm sorry. So
Sorry.
if you looked in your calculator and you looked for the cosine of 1/2, it would only give you 60 degrees. It would never give you the other quadrant. Where else is cosine positive in your unit circle?
4.
4. It wouldn't give you 300. It wouldn't give you that. Because we're going to restrict it so that its inverse will only go here. Now, let's just pick a point on this. Let's pick 60. Let's pick 60 degrees. Pi over 3. Its cosine is 1/2. When I invert this, I will be 1/2 pi over 3. So figure pi is like 3. So 3 divided by 3 is what?
1.
1. So I should find a point 1/2, 1. So here's my pi again. This is 3. So if I find the point 1/2, 1, uh, 1/2, 1, where am I?
No, it's just like
Well, technically, it's
Oh
just
no,
a
this
little
is
less than 1.
sorry, this is the regular curve. This is our regular curve. Did I give you the graph of the
Oh, yeah,
inverses
just-
on the next page?
Scroll down a
So
little
scroll down to the next page, if you will, and look for 1/2 and 1, and you'll be able to find it. Remember, pi is just estimated to be 3. Okay, so now, do you see how they're switching their range and their domains around? So
Yeah.
on a true inverse, all your range and your domains will switch around at the same time. So we went through 3 things, we restrict only these 3 things, because these are the ones we want your inverse for. Now what that buys us is when we say arc sine, arc cosine, and we're going to do a couple of those to see why we use these. Because when you look for an inverse, you get a true inverse. I thought I had them on your paper, but I guess I don't.
Maybe we could do some from our homework.
Now we'll do something here. So let's take a look at some of these. All right, let me just get a blank piece of paper here. Oh, there they are. You didn't get these. I don't know why you didn't get this. I think it probably got stuck to the other paper when they copied it. Because I have it. It probably just got stuck.
We're going to need our special triangles here.
Ah! What if you unrationalize this guy? What does this come out to be? 1 over radical 2. So let's just start like that. Is that good? Now, arc cosine means I need a restricted inverse. So find me first. Where is my cosine curve restricted? This is what I do. I don't memorize. I do this. Watch. Here's my cosine curve. Oh, I can't go backwards. Oh, I travel down. I stop. Where's my restriction? 0 to pi. Don't memorize it. Just visualize your curve. What quadrants do I want? 1 and 2. So I do this. I drop a triangle here. I drop a triangle here. 1 and 2. Oh, I want this to be positive. Which one do I use?
Use quadrant 1.
1. I don't want this guy. I use quadrant 1. So cosine x over r. What angle is this in here?
45.
45. So this will give me pi over 4. What angle? This is asking. What angle has a restricted cosine of 1 over radical 2. That's what arc means. An angle whose cosine is. An angle whose sine is. An angle whose tangent is. We could write it like this too. You could write them like these. You can see like a big arc versus a little arc. Like years ago, what they used to do is make a difference between the capital and then the small a. They no longer do that. Every arc is considered a restricted angle, regardless of what it looks like. So you return me one answer, pi over 2. If I said, I'm sorry, pi over 4. A degree, 45, yeah, unless I specifically said what it was. If I did this, arc cosine, negative radical 2 over 2, what quadrant would this guy be in? 2. So this is my 1, my radical 2, this is 45, so what angle would this be?
Oh, I see what you mean. It won't always be more than 90.
Yeah, this is the only one. Yeah, this is the one, cosine is the one.
135, right?
It'd be 135 or 3 pi over 4, right? Now, your calculator will give you this answer. Your calculator will give you that answer. Your calculator only gives you restricted answers. So you can kind of like verify your homework with this, with your calculator. All right, let's try another one. 135. I switched that around. Okay, arc sine. I want a restricted angle whose sine is same thing. Negative 1 over radical 2. Now, where is my sine restricted to? I don't remember this, so let me draw my sine curve. Here's my sine curve. Up, start here, go across, stop there, come down. Where am I restricted to? What quadrants?
1 and 4.
1 and 4. So out of 1 and 4, where is sine negative? 4. So this is the guy I want. This becomes, but here's the tricky part. This becomes a 45-degree angle. So what's my answer to this? My restricted, very good. Negative 45 degrees. My restricted domain is from negative pi to positive pi over 2.
Negative pi over 4, right?
Or negative pi over 4. And that's what your calculator will tell you also. It will give you negative 45 degrees. Okay. How about this? An angle whose tangent restricted is 0. Where is this restricted to? What quadrant? 1 and, so let me draw my tangent curve. 1 and 4. Oh, where is the 0? Where is tangent 0? Look at that, I can see it right here. Isn't it right here? Isn't it one of these? Isn't it y over x? So my answer is 0 radians or 0 degrees, whatever you want to call that one. Okay, so tonight I want you to make sure that you understand these restrictions.